Imagine the icy fortress of the Arctic suddenly cracking open, unleashing a torrent of cold air and snow that could transform your holiday season into a winter wonderland or a frosty nightmare. This isn't science fiction. It's the unfolding reality of a sudden stratospheric warming event, sparking one of the earliest polar vortex collapses on record. Buckle up, because we're about to dive into how this atmospheric upheaval is poised to blanket parts of the United States, Canada, and Europe with chilly blasts and potential snowfall, reshaping our weather patterns right through December and into the festive period. But here's where it gets controversial. Is this a sign of climate change amplifying winter extremes, or just Mother Nature's unpredictable dance? Stick around to explore the details. First off, let's break down what's happening. Sudden Stratospheric Warming, SSW, is underway, kicking off this premature polar vortex meltdown. According to the latest predictions, this disruption will ripple down to affect lower atmospheric levels, ushering in frigid temperatures and snow across select regions in the US, Canada, and Europe. Picture it as a powerful atmospheric shakeup that could make your winter outings more about snowmen than strolls. To truly grasp the polar vortex and its mechanics, you don't need a degree in meteorology. Think of it as a massive, swirling, low-pressure barrier encircling the polar areas, stretching from the ground up to the stratosphere. That's over 50 kilometers, or about 30 miles high. It's like an invisible dome, trapping the bone-chilling Arctic air inside. For clarity, we divide this vortex into two key layers, the upper stratospheric part and the lower tropospheric part. They function somewhat independently, but together orchestrate the broader winter weather systems that influence our daily lives on the surface. We keep a keen eye on its strength, shape, and dimensions, categorizing it into two primary states to make sense of its behavior. When the polar vortex is robust and steady, it maintains a tight grip on that polar cold, keeping it confined to the far north. This often leads to milder winters across much of the US, Europe, and other temperate zones, sparing us from the full brunt of winter's fury. On the flip side, a complete collapse or weakening of the vortex means the cold air escapes, spilling southward and delivering genuine winter chills to mid-latitude areas. Visualize it. A disrupted vortex acts like a faulty lid on a freezer, letting the icy contents flood out. Think of past examples where this led to record-breaking blizzards in the northeast US. If you're dreaming of a classic winter with crisp air and snowy landscapes, a weakened or disrupted polar vortex is your ticket to higher odds of that authentic seasonal experience. For the ultimate visual aid, check out our high-resolution video below. It renders the polar vortex in stunning 3D, forecasting its current state and the onset of disruption. The key insight? It's one interconnected atmospheric system, not isolated pockets of weather. For instance, it's not merely a single storm system hitting the northeastern US. It's a vast circulation that can influence global patterns. And this is the part most people miss: how these stratospheric shifts directly trigger surface-level changes. Let's delve into the current SSW analysis and its effect on the polar vortex. Sudden stratospheric warming in action, examining the latest data from the mid-stratosphere, around 30 kilometers or 18.5 miles up. The polar vortex is visibly warping. Normally, it forms a neat circular shape, but now a bulging high-pressure zone is encroaching, distorting its structure. Temperatures around its core are climbing too, far from the icy norms. Typically, the vortex's cold heart dominates a wide area over the North Pole, but displacement is warming the polar expanse unusually. Pressure anomaly maps at this level reveal the vortex's core holding steady with low pressure. Yet a growing high-pressure anomaly is complicating things, much like a storm disrupting a calm sea. A 3D view of the polar vortex underscores this deformation, showing its mass buckling under the strain. This is just the inception. Forecasts predict the high pressure and warming to burrow deeper, sapping its power. To gauge strength, we monitor the winds it generates. The more orderly the vortex, the fiercer the winds encircling its center. Recent analyses and projections highlight a dramatic erosion of the vortex's winds and temperatures over the coming fortnight, as high pressure expands and warming intensifies. A critical marker is the zero line, signaling a wind shift from typical west to east westerly to east to west easterly flows, which would classify this as a major SSW. Even without that full reversal, significant surface impacts can emerge if disruption is severe. Consider how milder winters can flip to snow-blanketed holidays. A schematic diagram illustrates the SSW process, depicting pressure shifts across atmospheric layers over time. We're currently in the early stages, around days -5 to -7, where energy surges disrupt the vortex, fostering warmer, higher pressure pockets in the stratosphere. This top-down collapse frees cold air to descend, affecting the US and Europe alike. Peak disruption is anticipated around Thanksgiving, heralding a major shift into meteorological winter. Forecasting the polar vortex's breakdown charts indicate major surface repercussions are 2 to 3 weeks off. Targeting early December. The climax of warming and disruption is slated for late this month, approximately the 25th, plus or minus a day. Visuals show a formidable high-pressure anti-vortex in the mid-stratosphere, driving a warming surge that deforms the main vortex with temperature waves. Temperature anomaly forecasts reveal extreme warming up to 30 degrees Celsius above normal in the mid-stratosphere, highlighting the event's potency. Interactions between the vortex and high-pressure system are evident in wind forecasts, showing energy siphoning that weakens the structure. A 3D projection for month's end depicts a severely fractured vortex with energy depletion across its form, though full surface effects may lag. Transitioning to lower levels. How might this manifest in our daily weather? We seek signs of stratospheric energy trickling down. Forecasts at the lower stratosphere, around 20 kilometers or 12.4 miles, for the 28th reveal high pressure and warming, pushing the vortex aside, signaling a swift downward influence. Broader pressure anomaly graphs for the lower 50 kilometers, 30 miles, track this upward energy wave, triggering the SSW. Then its gradual descent, linking stratosphere to surface. These events historically impact ground-level weather, so let's draw from history for insight. Anticipated surface weather shifts. Composite images from past SSWs show surface pressure patterns 0 to 30 days post-event, with high pressure dominating the pole, displacing lows. This blocked pole weakens the jet stream, spawning low-pressure systems from the eastern US across the Atlantic to Europe, unlocking Arctic cold toward mid-latitudes. For example, the 2000 event led to a snowy winter in the US Midwest, illustrating real-world consequences. Our research uncovered only 3 such early-season SSWs in the last 70 years, 1958, 1968, and 2000. 2 involved full wind reversals, 1 a mere weakening. December temperature anomalies post-event reveal a frigid corridor through Canada and the US, except the Southwest, with milder cooling in Europe. As the 2025-2026 winter approaches, we'll monitor if this echoes. Preparing for chilly winds and snow. SSWs typically channel high pressure from the stratosphere to the surface, destabilizing patterns and liberating polar cold to the US, southern Canada, and Europe. In many cases, at least, early December surface pressure anomalies forecast high pressure engulfing polar areas, shoving the vortex's core into North America. Its counterclockwise spin generates northerly flows from the Arctic into Canada and the US. With southwesterlies over the North Atlantic, focusing on North America, a 500 millibars, about 5 kilometers or 3 miles up, forecast for December shows the vortex core entrenched in eastern Canada and the northeastern US, sweeping the continent. This sustains northerly cold influx from western and southern Canada, signaling a frosty, snowy meteorological winter start for the US and Canada. Temperature projections for early December hint at a potent cold outbreak across northern, central, and northeastern US, aligning with the vortex's pumping action. Scenario examples depict cold air plunging southward, potentially blanketing areas widely, though these are illustrative, not guarantees. Extending to late December, anomalies suggest persistent cold over southern Canada and the US, with stable northerly flows drawing deep polar chill during holidays. A vortex core over Canada could stabilize this, boosting white Christmas odds across US regions. Extended forecasts in mid-late December envision significant cold releases over southern Canada and much of the US, tied to the vortex's strength. Another plausible outcome post-SSW. Snowfall outlooks for December project widespread coverage from Canada into northern, western, eastern, and even southwestern US, with plains snow expansion. This ensemble view supports enhanced snowy holiday potential, reaching southern areas more than recent years. Historical precedents bolster confidence. For Europe, an initial North American vortex focus might bring milder westerlies early December, but extended scenarios show potential shifts. High pressure shifting north, lows south, creating easterly cold flows for beast from the east conditions. We'll track this closely. Stay tuned for global pattern updates. Bookmark us. If spotted via Google Discover, hit that like for more forecasts and nature insights. Main visuals courtesy of Weatherbell via a commercial license. Don't overlook our latest Winter 2025-2026 outlooks. Winter 2025-2026 final outlook, a colder season than expected, driven by polar vortex dynamics. Link. But here's where it gets controversial. Some experts argue these early SSWs are becoming more common due to human-induced climate shifts, potentially leading to erratic winters. Others see them as natural cycles, unrelated to global warming. Do you believe this event heralds a return to harsher, snowier winters, or is it overstated? Could it even benefit ski resorts while challenging unprepared cities? Voice your views in the comments. We'd love to hear your take.